So hello everyone, this is Fluid Mechanics Laboratory and today we will perform an experiment which is about the flow meters. Actually there are different kinds of flow meters, but today we will focus on a special kind of flow meter which is called the Venturimeter. So a Venturimeter is a device which is basically used to determine the flow rate, the discharge in a pipe. So as you know, the flow rate is represented by Q, which is a volume of fluid passing through a section in a unit time, and its unit is meter cubes per second. So the basic purpose is to determine the flow rate, the discharge in this system. So as you can see, this is on the board, you can see the definition sketch of the Venturimeter. So basically we have two sections, section 1 and 2, and the flow is from right to left. And here at section 1 we have velocity 1, V1, and we have a certain diameter of the pipe, which is, in this experiment, we will use 28.4 millimeters. And then, as you see, the pipe goes and it converges here, and it reaches to the second section. It's a throat section. As you can see, the diameter is reduced. So, it is given as 22 millimeters at section 2, and we have a velocity again. So, and after that section, the pipe just diverges and it reaches to the original pipe diameter, and of course within this whole system the total discharge remains constant. So in order to write the basic fundamental laws, first we can write the energy equation within this system between sections 1 and 2. As you know, the total head at section 1 has to be equal to the total head at section 2 plus a certain friction loss. But within the scope of this experiment, we ignore the total head losses. So there is no friction loss and there is no minor losses. So here, due to this reduction in the cross-sectional area at this part, due to this converging part, there has to be some minor losses. And also, inevitably, there are some friction losses as well as the flow is going from section 1 to 2. But as I said, we ignore the head losses in this experiment. And also, the Venturimeter that we are going to use in this experiment is a horizontal type of Venturimeter, and therefore this elevation terms are cancelled out as well. So in order to express the energy equation, we only have the pressure head, which is P divided by gamma, and gamma is the specific weight of the water, as you know, which is, and we are using water in this experiment, and gamma water is 9.81 kilonewtons per meter cube, and pressure head plus the velocity heads, the kinetic energy of the water, and it is represented by V squared divided by 2G. So the energy equation becomes the pressure head and velocity head at section 1 has to be equal to the pressure head and velocity head at section 2. So this general energy equation, if we ignore the head losses, the friction and minor losses, it is just simply the Bernoulli equation, which is the total head has to be equal at both sections. So this is the energy equation. And as you can see, as I said before, at the beginning of the experiment, there is a reduction in the diameter here. So there is a contraction part at the second section. And since there is a contraction, the velocity 2 has to be bigger than velocity 1. So the flow is accelerated at section 2. And therefore, if you look at here, there is a certain pressure and velocity head at section 1. And here, at section 2, the velocity head is increased. The kinetic energy of the water is increased at the second section. And thus, it has to be compensated by a reduction in the pressure. If the velocity head is increased, of course, this pressure head has to be decreased in order to satisfy the Bernoulli equation. So there has to be a pressure difference between the sections. And how we can understand this pressure difference? If you look at here, we take some tubes from the system and we determine the water rise in the tubes, in the manometer tubes. And here at section 2, it is H2, and the first section, it is H1. And after writing the energy equation, we can write the pressure distribution equation at these tubes, and as you can see, we can assume a hydrostatic pressure distribution, which means the pressure at section 1 is gamma times the depth, which is the water rise, the depth of water in the first tube. And for the second section, of course, the pressure distribution, hydrostatic pressure distribution, can be expressed as gamma water times the second height of the water. So this is our second set of equations. And finally, we can write, after energy and pressure distribution equations, we have to write continuity equation. Of course, the upcoming inflow has to be equal to the outgoing inflow, which means the velocity and area, the multiplication of the velocity and area at section 1 has to be equal to the V2 times A2. So this is the continuity equation. So basically we have three sets of equations, and what you are going to do in this experiment is you will rearrange all these four equations, basically all these three equations. You will rearrange all the equations, and finally you will find a discharge value within the system. And that discharge will be your actual discharge. And for this experiment, we will use this CD, which is the discharge coefficient, as it is given as 0.962, and it is a dimensionless coefficient, of course. After finding this Q actual from here, you have to multiply, from here you will find the Q theoretical, and you have to multiply Q theoretical with CD, which is 0.962, and you will finally obtain the actual discharge value. Why do we multiply this theoretical one with the CD? Because, as you remember, at the beginning I said we ignore the head losses, but of course in reality there exists a friction loss and a minor loss, and therefore we have to multiply that theoretical value with a constant. So that is discharge coefficient, and finally you will find Q actual. And now let us show you the experimental setup. So this is the experimental setup that we will use. As you can see, this is a complete system having a pipeline, and you can see the inlet part here. The flow is coming here, and it goes from right to left, and it exits the system from this part. And here we have some tubes. As you can see, we have some manometer tubes, and if you look at here, we have some different kind of structures inside this pipeline. We have bands, contractions, expansions, or elbows, like here. But within the scope of this experiment, we will only consider the contraction part, which is this part actually. So the pipe comes here from right to left, flow from right to left, and here at this part there is a contraction. So we will deal with that part, and we will take our measurements, our water rises from 7 and 8. From the 7th and 8th tubes, we will read the H values, which are basically these values, as we already mentioned. So this is going to be the 7th tube, and this is going to be our 8th tube, and we will read the H1 and H2 values, and we will fill this table after the readings. And what about the Q values? The Q values are arranged from this blue valve. We will arrange the Q values, and then we will read the values of the discharges from here. And the discharge, the unit of the discharge in this experiment will be liters per minute. You will use liters per minute, not meter cubes per second. So the Q values will be liters per minute. Therefore, you have to convert in your calculations this value into meter cubes per second. Don't forget to convert the Q into meter cubes per second. So, as you can see, we will give you 7 different Q values. We will start with 8, and then we will continue with 12, 16, 20, 24, 28, and 32. These will be your 7 measured Q values that we will give to you here. And then for each Q value, for each measured Q value, we will read, as I said, H values. So let's start with our first discharge value, which is 8 liters per minute. The first discharge is 8 liters per minute. As you can see, we arrange it to 8 liters per second, and then we will read the 7 and 8 tubes H values. So what is the value? It's around 420 to 410, right? Yes, 420 and 410.
I think 25.
Okay, 425 H1 here.
Yes.
This part, yes, 425, and the second one is 410. Yes, so this is for, by the way, the rise of the water inside these tubes are in millimeters. You will also convert these millimeters into meters. And this is for 8 liters per second. We are increasing our discharge to 12, and let's look at it. Let's read our H values for 12. So it is 12 liters per minute. The reading is 415 to 395. Right? Yes. Let's continue with 16. We are increasing our discharge. We are increasing our flow rate. So now the flow rate inside this pipeline system is 16 liters per minute. And let's read our value from 7th and 8th tubes. It is 405 to 370. And now let's continue with 20 liters per second. And let's read our values. 385 to 385, 340. Now the discharge is 24 liters per minute. And we read 370 to 300 millimeters inside the tubes. Okay, let's continue with 28. If we increase the discharge to 28, what are the H values? So it's 355 to 270. And finally, our final value, 32 liters per minute. Our final reading is 325 to 225. So we fill this table. We gave you 7 different discharge values, and we read 7 different H1 and H2 values corresponding to water increase inside the tubes. So now let's summarize what we did so far. So basically what we did is an experiment for a Venturimeter. So as we said, the pipe just comes here and there's a contraction part at the second section, which means if there's a contraction, of course the velocity will be increased. There's a flow acceleration at this contracted region. So we wrote the energy equation. Here we used a horizontal Venturimeter, which means, so as you know, these are the elevation terms, elevation heads, the pressure heads, and the velocity heads. So since we use a horizontal velocity Venturimeter, we can cancel the elevation terms out and only we have pressure and velocity. Also, as we already mentioned, we ignored the energy losses through the system. So at this contraction part, since the velocity is increased, as we said, the pressure has to be decreased. That was our aim. And in order to see that decrease in the pressure, we used these tubes and we read these data for given discharge values. So this will be your Q measured values. Once again, these are in liter per minute. You will convert them into meter cubes per second, don't forget. And these H values, the readings are in millimeters, and you will also convert these into meters. And you will make the calculations accordingly. So after writing the energy equation, we ignored the head loss, which means it's a Bernoulli equation actually. We wrote the pressure, hydrostatic pressure equation as gamma times, the gamma water times the H value at section 1 and at section 2, these two equations. And finally, the continuity equation. Of course, we have to satisfy the total discharge at both sections. So V1 times A1 has to be equal to V2 times A2. And here, I already mentioned, what you're going to do is you will rearrange this formula and you will find a Q value. And that Q value, the thing that you're going to find here, will be your theoretical value. This is your theoretical value. And since we ignored energy losses here, in reality, there is no such a case. In reality, there is always an energy loss due to minor losses or friction losses, but there is always an energy loss. Since we ignored this one, you have to multiply this theoretical value with a coefficient, which is called a discharge coefficient. And in this laboratory, it is 0.962. So you will multiply Q theoretical with the discharge coefficient, you will obtain the Q actual value, which will be your Q calculated one. So for each measured Q values that we gave to you here, for each value, we read these H values, and then you will find 7 values for the velocities at section 2, and correspondingly, after finding the velocity, you will just multiply the cross-sectional area at section 2, and you will find Q value. And this will be your theoretical one, and then you will multiply it with 0.962, and you will obtain Q actual. So first you will find the velocities, and then you will multiply it with the area, and then the discharge coefficient, and you will fill this table. So this is the table that you are going to prepare. And finally, of course, we have an experimental discharge value, a measured discharge value, and the one that you calculate. And at the last column, you will determine the percent error in terms of percentage between this calculated and measured discharge values. So in your report, you will prepare this table, and finally, you will draw a graphic, which is here. In this graphic, the x-axis, the horizontal axis, is the Q measured, which is in meter cubes per second, and the y-axis, the vertical axis, represents Q calculated one, which is this one, and it should be in meter cubes per second. And you will draw the graphic showing a comparison between the calculated and measured ones. And That's it. That is the end of the experiment.